professor at Oxford, but she's also director of the Isaac Newton Institute, and it was essentially under Ulrika's steerage of that the KE Hub was founded. So it's extremely appropriate that she tells us about some work that she's been doing on topological data analysis. So over to you, Ulrika.
Thank you very much for the introduction, Chris. Yeah, I hadn't quite ticked that this is historical, so I will be actually talking about somewhat recent work as well. But the Center for Topological Data Analysis was founded about 6 years ago, and it very much had this idea that we want to go from theory to applications and back to theory, and have this cyclic nature that Chris just mentioned. So when I write, because this is, the idea was tomorrow's pure mathematics, I thought I pinpoint what maybe this area, or our group in particular, has maybe contributed to the pure math side, or one aspect anyway. The most recent one are some new invariants for quiver representations. I put new in bracket because this is, it's a question of how, well, I think they are new. Let me just not apologize. So there we are. Okay, so let me start. And this is, of course, now, how do I forward? That's the question. Oh dear. There we are. The main tool in topological data analysis is persistent homology, and it's that aspect and that theory that has seen many applications and at the same time theoretical development. So let me just hopefully remind you, but if you haven't seen it, maybe this is a slide that takes the essence away. So what one does, do you see my cursor, by the way? Anybody? Yeah, okay, good. So one starts with some point cloud. Here it's in R2, and one wants to understand the shape. Of course, if you just look at the point cloud, you might guess it's a circle or coming from an annulus, these samples, but abstractly, it's just a discrete set of points. And topological data analysis tries to associate at different scales topological spaces, or more technically simplicial complexes, because we can compute with them. And so at this scale 0.6, we put an edge between any 2 points if they're less than 0.6 apart. And if we have all 3 sides of a triangle, we also put in the triangle, and similar with higher and higher dimensional simplices. So as the scale grows larger, you can see that we are building up a bigger and bigger space. And finally, of course, when the scale is too large, then we just see a big blob. Then what, theoretically, what we're doing is, we have sort of different time steps. This is represented by Z, and we include the complexes from one to another. So really we're thinking of associating to each integer a simplicial complex, and between these time scales there's a map of inclusion. And finally, one associates homology to it, which gets us into vector spaces. Now, vector spaces, I mean homology, we have one for every dimension. In dimension 0, it really just counts connected components. So we have plenty of them right at the beginning. But of course, at the end here, we just have one connected component, and that is the signature there. If we look at one dimension, then we'll basically look at cycles within our complex. So nothing here, no loops, but we are having this loop right here, which persists when we include this complex in here. But of course, it vanishes in this very big complex. So recording this one loop is this bar here. And actually the bars, each of the bars corresponds to a basis element, a dimension in the persistent homology we're working over field. So abstractly, we can think of this composition as really taking something, an integer. For integers, I have a vector space and I have these inclusion maps. Actually, on the vector spaces, they're no longer inclusions. They might be just linear maps. Sorry. Okay, so that's persistent homology. And there are two big theorems, actually. Let me go back because it's easier to explain. Two theorems, namely one is that if I move these points just a tiny bit around, just have a little bit of a wobble on the table, then the persistent homology, so this analysis, these bars only change by a little bit. So basically a continuity argument. And then the other thing is, it's not completely obvious that one should be able to track the vector spaces, find suitable basis elements so that I can represent them with these bars. But more importantly, these bars are complete invariant of the persistence module. Okay. Everything that I possibly would want to know about this persistent module that I get by this composition is encoded in these bars. Okay. However, when I said you can wiggle these points and nothing major happens, that's true. What is also true is that if I just plonk one tiny point in the middle right here, it will have a huge effect. Namely, it will, for example, make this hole here, which was tracked by this bar, basically half the size. So it's a really drastic thing if I put just one point in the middle of this point cloud. So here are these, just trying to reformulate those two ideas. And the problem is that noise, namely this one point in the middle of the loop, do give us a much weaker signal. So this is a problem when you want to do data analysis with real data. And to overcome that, there is something called multi-parameter persistent homology. So before we sort of grew the distance between the when each the points sort of saw each other, we grew the epsilon distance. But now we want to grow something else. So here we have two circles and samplings from them, one bigger, one smaller. And of course, there's inside there's some noise. Now, I think we all still agree that two circles and they are prominent and the interior points are noise points. In order to deal with them, we can introduce another threshold, not just the distance of points between them, but another threshold, namely how dense the point cloud is around any point. So for example, this point here is clearly isolated. So ideally, I want to disregard it. On the other hand, it's not clear, for example, immediately whether I should disregard these points and at what threshold should I put my level of density to discard points. So the idea is that one doesn't do that, just like in persistent homology. One doesn't pick a distance to build the complex, but one consider all distances. Here we consider all densities. So we now consider all densities and all distances. And that means we are building up really a multi-parameter persistent complex. So in other words, given a radius and given a distance, so here n is actually 2, I build my complex with the information of those two and then build and take homology. So again, as a composition here, we get something that's called a persistent module. Okay, so this is and was already introduced about 20 years ago by Carlson, Zamorogin, and we don't have bars, which were really helpful in persistent homology, or are really helpful. So one tries to find some other invariants of this multivariate persistent homology. So the first one is actually the so-called rank invariant by Carlson, Zamorogin. So for any density and radius, we just look what happens if I take the image at that particular density and radius, and what happens to the vector space when I include it into the vector space associated to some larger density and radius. Actually, yeah. So it's this dimension that I then record. So lots of 2 by 2 by 2 by 2 grid of natural numbers. And a student of mine sort of refined this or derived from this idea another invariant, namely a multiparameter persistence landscape. And basically, it's a collection of functions, one for every k. And really, it associates, it tracks the ranks between these functions, between these vector spaces, only in a slightly different way, namely, it really defines a function which we can then integrate and so on. So this is, those who are familiar with this, is just a multiparameter generalization, really, of the landscape in one dimension, and it sort of takes the landscape in the direction parallel to the diagonal, just adding on the diagonal direction. Okay, not too important for ideas here. It's a new invariant. It can be added and taken average. We can do statistics with it, and that is the advantage compared to the rank invariant by Carlson and Zamorogin. And indeed, we were able to apply these things in various cases. So here is just an idea how that might work. Here you have our two circles again, and these are the persistence landscapes that are associated to this first picture. The first one counts how many circles we see at different co-densities, I should really say, and a radius. And indeed, this flame here depicts this smaller circle at lower radii and higher co-density, lower co-density, and this one here, this flame here, sees this bigger circle, slightly higher radii I need in order to see the circle, and I can allow myself bigger quarters. And so then the second picture here, where we have basically three circles, all similar, we can see it happening in these three different landscapes. It's a good way of seeing these cycles, and indeed we have applied it. I think I might have mentioned something like this in a previous talk in the K-Hub. Here's an application to immune cells and tumor. We analyzed some pictures that we get from immune cells, here CD8, FOXP3, and CD68, and we're able to analyze them. And indeed, something the clinicians were interested, we were able to show that the density versus radius is quite similar to hypoxia versus radius, which they were interested because hypoxia is very difficult to measure and co-density is relatively easy to measure, so maybe. The point here, it has been applied, and indeed we applied it, the mechanism again in a recent Nature paper. So, Oliver Weipont developed this new invariant, and we were able to apply it. Now, back to theory, I think I'm going to stay a step yet further closer to, in some sense, to pure mathematics now. Namely, I want to reformulate this persistent homology really in terms of quiver representations. I basically already said that. What's a quiver representation? Well, what is a quiver, first of all? It's just a fancy name for a directed graph. And for us, directed graphs we are interested are really all finite. So in particular, the directed graph for persistent homology is just a string of points, and we have the forward arrows, and that's our persistent module. The graph underlying persistent module. For the multi-parameter, we just have a grid like this, a square grid, and arrows that are forward pointing. Now, what is a quiver representation? Well, it's just a map, really, that associates to every vertex in my quiver, in my directed graph, a vector space, and to every directed edge, I have a map between, a linear map between the two vector spaces associated to the vertices. And so we can form a category of representations. Of course, for every such representation V, we have a nice dimension vector, namely at every vertex, I just record the dimension of Vx. So examples that are important for what I want to say are the so-called identity representation on a subquiver. So I just take a subgraph and I associate just the one-dimensional vector space to every vertex in the subgraph and zero otherwise. And if I have an edge in the subgraph between two then also the endpoints are in the subgraph, and they will have been assigned F, and I just assign the identity as the linear map between these two copies of F. So that's very nice representation. Another one I will have to consider are so-called sub-representation generated at X. So just look at one of the vertices. It has a vector space Vx assigned to it. And then I just look at how that vector space is propagated throughout the graph, throughout the quiver, by the linear maps. So it's just the smallest sub-representation containing Vx. Okay, so there's representation theory. Representation theory tells us that as long as we are talking about a finite quiver, a finite directed graph, then every such representation can be decomposed as a direct sum, some multiplicity, and some collection of indecomposables. Now, it's always a good question, how many indecomposables do I have? And the point is, and of course, I would like it to be finite, but this only happens if the underlying graph is so-called a finite union of simple Lace-Dinkin diagrams, namely type A, D, or E. So in particular, our persistence module, the very first one that was just a string, is of type A, which is a good one, has only finite, namely all these bars that can occur. And the multigrid one is not. So in other words, the multi-parameter representation theory is really of wild type. Okay. Well, we don't want to give up yet, because maybe we don't completely need to understand each of these modules. We just want to extract some invariants, like the rank invariant and the persistence landscapes that we saw before. So this is an idea of trying to find stronger and new such invariants. We're going to borrow some from algebraic geometry or geometric invariance theory. So let me just very briefly explain where this comes from, or how it's constructed, really. I take a so-called central charge, which is just an assignment of a real number to every vertex, okay? And then the slope is taking the dimension really in this weighted way. So I just take the weighted dimension at every vertex, put that in the nominator, and mod out by just simply the sum of all the dimensions at every vertex. And this function mu is called the slope associated to alpha. And then we have various definitions. We call something as semi-stable, stable if every sub-representation has slope less than the full representation, and stable if it is strictly less. These are more important for geometric variance theory, but I just want to mention them because they are important in terms of the theory. Namely, this theorem that we get is that as long as the quiver is finite, and it can just be any finite graph, directed graph, then every non-zero representation admits a unique filtration like this, such that the quotients have slopes that are decreasing. So the semi-stable comes here, and this is important theoretically, but for us, the most important thing is that there's a unique association of this filtration. And of course, once we have this filtration, we can define the quotients. And so this definition of an HN type makes sense. Namely, I just associate these dimension vectors to all these quotient representations. So it's a big thing, but it's a clearly defined invariant of my representation of the quiver. Okay, so that's a definition. I won't try to interpret it, but it's well defined, and we know that from algebraic, from geometric invariance. Now, I will say something. I can, of course, I shouldn't emphasize. We have such an HN type for every central charge, for any weighting that I put here. Okay. Now, we say such a weighting central charge is complete if the HN types distinguish between isomorphism types. Now, that's not going to happen very often. But the interesting part, if alpha is complete, then every indecomposer representation is alpha stable. That's a theoretical result. Right, so the only type that we are interested where it actually happens, that it is complete, as the type A. And I'm just going to quickly go through. One can even classify all the slopes, sorry, all the charges alpha when that is actually, when alpha is actually a complete invariant, the HN type associated to alpha. Namely, I have to just assign weightings that are decreasing on my points, on my quiver. Okay. And similarly, one can get complete charges also for these other Dinken graph types. So, but of course, for the other ones, we cannot. And so we tried to come up with some other invariants that had some meaning, and we were able to compute. So here's the skyscraper invariant, which is a new one. What we look at, we take our central charge to be actually something very, very simple. Namely, it's a delta function You pick a vertex y and just say this central charge is 1 at y, but 0 everywhere else. So it's really picks out this one point. And then we have a proposition, namely we can completely understand what happens at with this central charge, namely the associated HN filtration. Well, it will be basically the whole thing, or at least the one generated by Vx in the top dimensions. And at every other earlier stage, we have some sort of filtration of this vector space at x, namely smaller ones here, the Vx, and the module, the representation is just generated by what happens at x. So really, an emphasis here to make, we can sort of the filtration sort of filters what's happening at x, and then at the last stage just adds everything else that might be in the V to start off with. I won't go through the proof. It's not very difficult. It's just using the conditions that we have in the HN filtration in the theorem. Okay, so then the skyscraper invariant we define to be, well, I take the collection, it takes the delta function for every vertex in my quiver, in my graph, and look at the HN invariance. Now, that is actually a complete invariant on the H representation category of type AN. But we had this other invariant that in multivariate persistent homology, namely the rank invariant. Remember, that was just assigning the rank between the image of one location to the map into another location. And well, we can just generalize this now here by looking at these modules generated at one vertex. Namely, we take that, propagate it throughout a quiver, and look at what happened at another vertex y. We take the dimension of that image, and that clearly generalizes the rank invariant that Carlson and Zamorodian came up with, and to all quiver representation. Okay, and then we were able to show actually that's our skyscraper invariant, which looks at every skyscraper for every vertex, is actually strictly stronger than the rank invariant. Okay, that was one of the things. Now, I believe my time is actually running out quickly. Let me just say that there have been other developments in multi-parameter persistent that looks at the generalized rank invariant, and indeed we have generalizations of those to quiver representations and various theorems there. I have to put in the references here. This is a paper that I was mainly talking about. And since then, our student Mark Weston has also proved that there's stability for these HN skyscraper invariants, and also that they're computable. Okay, finally, one more remark. Reflections on pure versus applied. I do think we have been able to go very much between the pure and the applied, but of course there's a question of how far you go, and can you indeed, is it enough to appear in an applied journal, or even a general science journal, or in similar with pure, or is it actually a little bit further, namely that you answer, say on the pure side, questions that have come from pure mathematics, and finally. And so I want to take obviously won't talk about it now. I just want to mention that actually Poltorevich and Shelukin have been able to use
some noise coming. Could you stop it? So carry on, Ulrika.
Just finishing, they have been actually able to use the idea of persistence homology to apply to symplectic geometry and Hamiltonian flow of diffeomorphism. So there's possibly an even purer application of applied mathematics. So thanks.